question mark next to acetone. Why did I choose specifically to put this in acetone when I could have saved my acetone and just put it in distilled water? Why did I use my expensive organic solvent versus just using good old-fashioned cheap distilled water? Let's talk about why. So let's look at some of the intermolecular forces in both of these compounds. And also let's look at what type of solvents they are. This acetone is known as a polar aprotic solvent. This water is known as a polar protic solvent. Okay, so let's identify the three words in this chemical concept, I guess. So first, let's look at solvent. Both of them are solvents. That's why solvent is in the word. Both of them are polar. That's why polar is in the word. Let's see why both of them are polar. Now, if we look at this molecule here, this ketone, let's look at the electronegativity in this ketone, this acetone. That's a carbon right there. This carbon, that's the carbon of the ketone. That's the oxygen. That's a carbon of the carbonyl compound. There's a carbonyl here. Anytime you have a carbon doubly bonded to an oxygen, that's a carbonyl. That's a carbon of the carbonyl. That's the oxygen. Which one's more electronegative? The oxygen is. Why do we know that oxygen is more electronegative than carbon? The closer any atom is to fluorine on the periodic table, the more electronegative it is. Oxygen is closer to fluorine. Oxygen is closer to fluorine than carbon is on the periodic table. That's why oxygen is more electronegative than carbon. So the electronegativity goes that way. We draw the electronegativity arrows. This means that oxygen has a partial negative charge and carbon has a partial positive charge. So that means that this double bond between oxygen and carbon is a polar bond because the two atoms involved in that bond have a partial charge. Same thing for this carbon over here. This oxygen-hydrogen bond. Oxygen is closer to fluorine on the periodic table. Therefore, oxygen is more electronegative than hydrogen is. So it's going to have a partial negative charge associated with it. Hydrogen is going to have a partial positive charge associated with it. So this bond here, this red bond, it's also going to be a polar bond. So we see that both of these molecules are polar because they have at least one polar bond in them. So we can see that one is polar and that one is polar. So we can see why polar is in both words. The only difference between the words, and this is a very interesting part of the whole video, is why does this one say protic and why does this one say aprotic? Well, let's think about this. Anytime they say protic in the polar protic solvent, they're referring to hydrogen bonds, hydrogen bonding, because the protic part means a polar protic solvent is going to exhibit hydrogen bonding. Or what I mean is you're going to have oxygen, fluorine, I believe. I think chlorine can be connected. I think nitrogen can be connected. If you got any of these atoms directly connected to hydrogen, then that's going to be a H bond. That bond between the two is going to be a H bond. And what I mean is, like, if all these atoms right here, if they were equal to, I guess you can say A, right? Well, then if you have A connected to H, that bond right there is a H bond. So if you have any bond where A is connected to H, the bond that exists between A and H is going to be an H bond, a hydrogen bond. And oxygen, and A can be oxygen, fluorine, chlorine, nitrogen. I think it could be more or maybe less of these, but maybe definitely these, because these are very electronegative. And notice, oxygen, chlorine, and nitrogen are very close to fluorine. And of course, fluorine is the most electronegative on the periodic table. So they're able to really polarize that bond and create a hydrogen bond. So let's go back to over here. Now, notice, if you have a carbon connected to an oxygen, that's not a hydrogen. That is not a hydrogen. So there's no hydrogen bonding, no H bond in this molecule. But this is a polar bond. And don't get me wrong, polar bond does have net charges, just like a hydrogen bond does. But a hydrogen bond, okay, these are two intermolecular forces we're talking about, dealing with here. Now we're looking at a H bond versus a polar bond. Or what is it? Dipole-dipole. A dipole-dipole. You see it referred to a dipole-dipole. Dipole-dipole interaction. These are two what I'm getting at is these dipoles, this negative positive and this negative positive, they have a certain strength associated with them, like, physical chemistry, physics, and all that stuff. They have a certain pull associated with them, or strength. And what I mean is, this negative charge can attract positive charges, this positive charge can attract negative charges. Same for these two. And they have a certain strength associated with them. And these two have a greater pull than these two. The H bond is a stronger intermolecular force than the dipole-dipole interaction. And I'll say it one more time. The H bond has a stronger attraction. It's a stronger attractive force than the dipole-dipole intermolecular force. So when you look at these two intermolecular forces, you got to understand that the H bond is more powerful than the dipole-dipole bond. So, okay. So let's talk about this. Now, you have to understand this. If we're in this situation where we have these two submerged in this ketone, the nucleophile is going to be attracted to the positive charge in that ketone if it was submerged in the ketone, and it is submerged in the ketone. Same thing for the situation if instead of putting it in the ketone, I put it in water. The lone pair, that negative charge on the lone pair, it's going to be attracted to that positive charge associated with the hydrogen. So you got to think about this. You got a situation where two things are holding up the nucleophile from doing what he's trying to do, perform the nucleophilic attack. He's trying to use that orange lone pair to attach to the carbon A, the electrophile. Perform the nucleophilic attack. Now, you got to think about this. Now, only thing that's holding him up from doing that, or one of the main things that's holding him up from doing that, is a solvent, because it's surrounding him. So you're looking at a situation where you got this atom right here. If it were submerged in this atom, it would be pulling at the nucleophile. So it'd be trying to attract that. It'd be trying to have an attraction on that lone pair, because it's attracted to it. It's negative, positive, negative. It's like attractive magnets. In contrast, and I did choose to put the nucleophile and the electrophile. I did choose to dissolve these two and the ketone. And the reason I picked it, because this same situation where these two attract each other, it happens right here too, because that carbon, that partial positive carbon in the carbonyl, it's going to be attracted to the nucleophile just like the water would be in that situation. So the thing is, you got to pick. Okay. Do I want to put now? Both of these have an attraction, but the carbon of the carbonyl, which has a partial positive charge, is attracted to the negative charge of the lone pair on the nucleophile. It's attracted to it. In the other situation, this hydrogen with its partial positive charge is attracted to the green lone pair, and the oxygen's, this oxygen's nucleophilic lone pair. So you have to pick the situation that's going to hold him up less, because it's going to make this happen faster. It'll be better for the situation. It'll hold him up less. It'll be better for him in this situation, because, he'll get to do what he needs to do, his nucleophilic attack. So we pick the ketone because its dipole-dipole intermolecular force is weaker than the H bond force, because the H bond force is stronger. If I pick this, if I put it in water, it's going to slow him down even more, and it's going to make my reaction even more difficult to happen. But in contrast, if I put the ketone, it's going to hold him up less because it's a weaker force. It's going to be attracted to him less. It's going to be attracted to the lone pair of the nucleophilic oxygen less. The H bond would be attracted to the orange lone pair of the nucleophilic oxygen more. It would have a stronger attraction. Therefore, it'd make it less likely to happen. So this is why I picked the ketone as the solvent, because it's going to make the Sn2 reaction happen faster and better. So that's why, and you'll see your professor say in an Sn2 reaction, we prefer to use a polar aprotic solvent. We prefer to use a polar aprotic solvent. That's what he's going to say most of the time. And I think they call this whole effect, when you put it in water and you slow down the nucleophile, whatever nucleophile you're using. In this case, we're using this hydroxide, and our nucleophilic atom is this oxygen with its orange lone pair. But whatever your nucleophile is, if you put it in a polar protic solvent that has hydrogen bonds, this whole process of slowing the nucleophile down, I think that you'll hear them refer to it as savolysis. This whole process, this whole conceptual imagination, if you were to imagine it, the whole process, the concept, you were to imagine water surrounding the nucleophile during its nucleophilic attack. If that picture in your imagination is called savolysis. So that's what they'll refer to that to. So this video turned out to be a lot longer than I expected it to be. So I'm just going to pick up in the next video about the potential energy diagram of the Sn2 reaction.